Thank you all for coming. This is the SOLIDWORKS Thermal Stress from Beginning to End webinar. I'll be one of your hosts today, Shaun Bentley. I'm a senior simulation specialist and been with GoEngineer and SOLIDWORKS in general since 2006. We've also got Sam Oanes with us today. He's been using SOLIDWORKS simulation for about the last 5 years now. We've got a lot to cover today, so let's get rolling. On the agenda, we're going to start with covering some of the basic tools that are available to you in different simulation packages, from SOLIDWORKS Simulation Standard all the way up to Pro, Premium, and Flow. Then I'll talk a little bit about some thermal expansion fundamentals, things that we'll really need to understand before we dive into a specific example. The different SOLIDWORKS simulation packages offer a wide breadth of functionality. The Simulation Standard gives you access to the static analysis tool, which we're going to use quite a bit today for running structural analysis and calculating stresses. In the Pro tools, you have access to vibration and thermal studies. One of those studies we'll be using quite a bit today as well. And then all the way up at the Premium gives you access to more vibration and some nonlinear tools. But really to narrow this down to some of the key tools that we're going to be using. These are the topics that are important for running thermal stress studies. Also, later on, Sam will show you SOLIDWORKS flow simulation, where we'll integrate the thermal results from that flow simulation into another structural study to calculate those stresses. What I'd like to talk with you next about is some thermal expansion fundamentals. Where do these thermal stresses come from? And a couple of the important details, I think, for you to see is going to be from bonding components together that have different thermal expansion coefficients. Here you see I have got a part that has a thermal expansion coefficient of 0.001. Here's another one that has a 0.002, so you see this one expands by more. And you can see the bonding stresses that occur between those two. And also, whenever you have non-uniform temperatures, here's that same expanding material, but it's hot in the center, cool on the outside, because most of the heat's getting generated from the center. We can kind of see it's expanding, kind of bloating, and that's generating some of those stresses. So I want to give you a little demonstration rather than just showing you a bunch of slides here. If I create a quick little study, this would be a static study just to see the stresses, and I'll put some simple fixtures on here. We're going to expand both of these blocks, these disconnected blocks, and if I put roller sliders on the back end of this, and then I put temperature loads to both of the bodies. I'll just do a box selection to grab them both. I'll heat them up to 100 Celsius, hot enough to boil water. If everything started out at 100 Celsius, we wouldn't see any expansion. So the starting temperature also makes a big difference, and I can set that under these thermal effects. Okay, I'll key in 0 for the starting temperature. And finally, we're just going to check the material property here to make sure that it actually has a coefficient of 0.001, and there it is. So looks like we're good to go. So I'm going to run this. We can see these two blocks just expand naturally. Now, and since they're disconnected from each other, since there's no connection between the two, you're going to see that we don't generate any stresses from this. So you can see the stress levels, they're pretty much 0. And if I look at displacements, this part was initially 40 millimeters long, and since I applied a 100-degree temperature delta to it, you could probably do the math in your head to figure out how much it should expand by, at least in this 40 millimeter direction. 100 times 0.001, you could come up with a 4 millimeter overall displacement. And similar here, this should expand by twice as much, and indeed it does. So now the real interesting stuff though comes when you actually bond different expanding geometries together. So here I've actually just put them together and run pretty much that same exact test. And when I do that, then now I get some contact stress. Now the stresses are no longer 0 here. Now also here in this quick demonstration, I wanted to show you if you apply non-uniform temperature distribution to these. Here I've set up a quick thermal study that shows the temperature distribution sectioned out. And it was just based on applying a heat power to this block and then some convection coefficients to the outer surface so it cools on the outside. And I can take these temperature results and then plug them into a static study and then see those expansions happen from those, and then therefore those outer stresses. We're going to get into the weeds on some of these, how to set up some of these studies throughout this webinar. but just wanted to give you a sense of where some of these stresses are really coming from. Now, a little more background information too is available. We shot a webinar probably a little over a year ago on the SOLIDWORKS Thermal to calculate those temperatures. In that webinar, we cover some differences between the SimPro and flow simulation on things like convection and thermal resistance. That webinar is available on YouTube. Would be a good one to view if you want to know more about the thermal side of what we're going to be covering today. One of the big topics, though, in this webinar is on convection. Just to do a quick review on some of the key differences that you're going to see in this webinar today are, for example, when we use the thermal analysis tool baked into Simulation Professional, we're going to have to prescribe convection coefficients rather than in flow simulation. We actually apply fan curves, see airflow, and then with this we can simulate the convection. So in SimPro, we prescribe them. We have to kind of take a guess that maybe the convection coefficient might be around 50 on these surfaces, whereas in flow simulation, we actually simulate those convections. You can kind of see here that the convection coefficient isn't 50 exactly. It's actually a variable. It's higher than 50 in some regions. It's lower than 50 in others. And this will be one of the key differences that we're going to point out again and again throughout this webinar. Now, with some of those fundamentals out of the way, we'll go ahead and get into some of our actual content here on this chip design that you see in many of these animations. Circuits can be complex. To try to structure a webinar around a circuit like that's this complicated, it won't fit into a nice, an hour-long package for you. So, of course, we're going to use a much simpler example here to just illustrate some of the fundamental principles behind setting up your own thermal stress studies. The gist of it is that we have a fan blowing over this chip, this microchip here. It has a ceramic coating on it. And that microchip is generating about 3 watts of heat, and that heat needs to get dissipated ultimately to the air. So we're going to try to set up this study and see what kind of stresses that we get between specifically between the contact region. We have this heat sink here, and we want to see what stresses do we get between the contact between the chip and that heat sink. So that's going to be one of the main focuses. Now, in order to set up this type of study, we'll have to do this in 2 steps. First, we'll run a thermal step to calculate those temperatures. And then we'll take those temperatures, see how it's heating up in the center, we'll take those temperatures and then we'll plug that into a structural study to figure out the stresses. The first way that I'll approach this, though, is with just a simple hand calculation. Now, I don't want to walk you through all the little nitty-gritty details of this hand calculation. I really just want to show you there are some key assumptions that we're going to have to make throughout a lot of the other studies that we're going to set up here. So I'm going to walk you through just a couple pieces of this hand calculation to figure out, what roughly would the stresses be between that chip and that heat sink. On this spreadsheet, I have these 2 sheets, one that takes care of the thermal step, calculates the heat transfer, where we have 3 watts. You can kind of see this little diagram here. We have 3 watts starting at the chip, and then most of the big red arrows, most of it's flowing to the heat sink to get to the air. That's the lowest thermal resistance to go this way. But then also some of it's going directly to the air. Some of it contacts that air directly. So we'll see these 2 main pathways that the heat takes. A lot of it goes left. I see about 2.2 watts of it goes left. Of that 3, about 3/4 of it goes left, and maybe about 1/4 of it goes to the right, goes out the side of the chip directly. One of the big assumptions I had to make when setting up the spreadsheet was, how effective is it at transferring the heat to the air? What should this convection coefficient be? And many times there's these little tables you might be able to find online that say things like forced convection, moderate speed flow of air over a surface, maybe use 100. If it's free convection, low speed, maybe use 10. Okay, so I have to make a decision where I want to plug in these numbers. Do I use 100? Do I use 200? Do I use 10? Okay. And that can make a big difference to the results. If I plug in 50, I get that chip temperature gets up to about 84 degrees Celsius. If I plug in 100, it drops that chip temperature down to 64. That's almost a 20-degree difference just by tweaking that one coefficient, that heat sink to the air coefficient. So you can see how sensitive my results are to these types of assumptions. So that's one of the main things I want to show you in this part of the spreadsheet. And then ultimately, I take the temperature results from my hand calculation. I'm going to plug those into a structural study. And on the structural side, I just need to account for how these bodies expand, similar to what I just demonstrated in SOLIDWORKS a moment ago. These two bodies expand, but when they're disconnected, they don't have any stress. It's only when I connect them that I see that stress, those stress levels. And one of the things I want to look at here is what that chip had multiple temperatures. Because the chip itself had a fairly low conductivity material, it was hot in the middle, cooler on the outside. Which of these temperatures should I use to describe this chip temperature in this hand calculation? Should I use the big one, the small one? Generally with a hand calculation you want to be conservative, and so you can see the heat sink, it expands by more than the chip. So the worst case condition here isn't actually just to use the big numbers that you see. The worst case condition is to assume the chip expands by the least amount possible and the heat sink expands by the most amount possible to give me the largest strain between the two. In other words, I'm going to use the smallest temperature for the chip and the largest temperature that calculated for the heat sink to describe that difference. And then based on that, I get a bonding stress in the ballpark of about 80 megapascals. And that's going to be a result I'm going to compare some of the other studies to in a moment. Now, if you're curious what happens if I do use this max temperature maybe instead, let's see how big of a difference it makes to the stress. And you see it makes it a little bit lower. All right, so 82.2 is the contact stress I'm getting based on this hand calculation. When I ran this hand calculation, I had to make a lot of assumptions, right? So I had to prescribe those convection coefficients. That's probably the biggest assumption. We're going to see how big of a difference that makes. But also I had to neglect complex heat transfer routes. Like you can see here, later on, when we run some of these thermal structural studies, I'm going to be able to account for some of the heat transfer pathways, the heat transfers through these little connectors down to the PCB. I'm neglecting that right now because it's just too complicated for me to try to account for. Then also some of the structural assumptions I had to make was I assumed the temperatures were uniform. And also I neglected any kind of complex deformations. You can kind of see the bending going on here, when really I was just sort of counting for the shear between the two bodies, not really accounting for any other complicated deformations that might occur. I'm neglecting those. Let's take one step forward, make some improvements to this by running the study this way. I'm going to use the static analysis tool, the structural analysis tool, part of Simulation Standard, to do the stress calculation for me. Now I still have to get those temperatures from somewhere, so that's where the spreadsheet still comes in handy to calculate roughly what those temperatures are going to be. So I'm going to take those same temperature values I got, but we're going to plug it into a structural study and see what kind of stresses we get. Open up this regulator chip design here. And for this study, I don't really have access to temperature results on like these guys and those and all that based on my hand calculation. So I'm pretty much just going to narrow this down to some of the stuff that I know, which is just through a configuration here. I've set it up to where I just have these couple of components bonded together, and we'll see what are the stresses on those guys. Now my first step to setting up one of these types of studies is to turn on the simulation add-in. I've already turned on my full-blown Sim Premium, so I have access to all the tools within that category. And I'll create a study. And since I'm just going to be using the static analysis, I'll go ahead and just call this, we're using Sim Standard basically in this one. I'll call it Standard Static. Not using any Sim Pro or Premium capability at this point. And my materials, they're already applied. I've got solder applied to connect the two bodies together, and I've got copper and a ceramic material for the other two bodies. Then for the component interactions, I'm going to assume everything is bonded together. It's going to bond together automatically, touching faces for me. Move down to fixtures, and how should I fix this thing? It's kind of like, well, when it plugs into something, it's going to be held somewhere down here at these locations. So it's tempting. Maybe I'll use just a roller slider similar to what I did in that earlier quick demonstration. I'll restrain maybe a couple of these faces like that. Now, if you're wondering, is this really a good way to fixture it? Because with these roller sliders, it's not going to allow this face to bend very much. Well, I'll show you a better way to fix it later on in the presentation when we include the PCB. But for now, I think this will be an acceptable way to hold it in place. And now we're going to apply the temperature load from our spreadsheet. So I'm going to go ahead and input temperatures as a load. And I've got two different temperatures I want to put in here for the chip and just the solder connection material. They're going to both be roughly at that temperature I showed in that PowerPoint here. Okay, 77.25 for those guys. And then the heat sink, I'm going to put at a slightly lower temperature. Yeah, I could probably just take the average of these two and just use that temperature for across the board, and it would be fine as well. But I'll go ahead and plug it in as you see here, 77.25. That'll be applied to those two bodies. And then to the heat sink, I'll use my body filter to be able to grab that body right from the graphics display. And that one's going to be 77.21. And finally, one more important thing is, like I showed you in that earlier example, it's important what temperature do these things actually start at. If I go to the thermal effects under the loads, I can say everything is going to start at 300K. It's like 80 Fahrenheit ballpark. Okay, it's a little warm, like a warm room there. Everything's going to be at 300K pretty much throughout this presentation here, just for simplicity. And with that, this study's pretty much ready to go. Let's go ahead and mesh it and see what kind of thermal stresses that we end up with in between those contact regions. The mesh I'm using today is going to be the blended curvature-based mesh, just using a default size for it. I'm not going to talk about mesh convergence and refining the mesh and all that. We're just going to basically just look at average stresses so that we don't have to belabor some of those points for this short webinar here. And ultimately, I get some stresses, which I'll make a couple quick customizations that I'll use for comparisons later on as well. Actually, I'll leave that set to red. And I'll bump the exaggeration scale up a bit too, so you can really see this thing bend. So I'll use a scale of maybe 200. So if I go ahead and animate that, you can see that the heat sink wants to expand by more than what that chip is expanding by. And so therefore, we end up getting this bending that happens. And it's tricky to account for this in a quick hand calculation. Then if I look at displacements, you can see I'll make a couple customizations to this too, again, just for comparisons later. And I'll use the same scale for that too. See, the top of it displaces by about 0.05 millimeters, so not much. And despite that, we get quite a bit of stress. If I look at the average stress on some of these faces, I have a nice value I can compare to for later. And I've created a sensor that probes that average stress, so I don't have to probe it after each and every run. These sensors are really, really handy. If I go ahead and edit this guy just to show you what it's doing here, it's taking simulation data, von Mises stress, and it's probing the average on this face. I've set it up to grab that connecting face there on the microchip. So it's giving me the average stress there, and that's right around 86.4. So that's what I'd like to compare that hand calculation to at this point. So we made a little bit of an improvement, I'd say. We've reduced some of our assumptions. So before we saw 82.2, we got a larger stress this time, 86.4, because now we're accounting for some of those more complex deformations. Okay, stuff that my hand calculation I wasn't really able to account for. I was just doing this straight expansion and seeing what kind of normal stresses I'd have based on that pure expansion. So for the next study, I'd like to couple these two tools together, the SOLIDWORKS Simulation Professional thermal analysis with the same structural step that I just showed you a moment ago, but with some extra geometry added to it. Okay, because with this thermal analysis, I can account for more complex heat pathways. Okay, so our temperature distribution will be a little different. And plus, we'll also be able to account for non-uniform temperatures. The fact that the chip will be a little hotter in the center than it'll be on the outside, we'll see how that non-uniform distribution, what difference that can make to these outer stresses on that chip as well. I'm going to go to a fuller model here, because now, like I said, we can account for some of these additional heat pathways. Now, in this example, I don't actually need the body for this fan. It's in there more as for the flow study later. For this thermal analysis, it's not going to really make that big of a difference to include that body. But really, it's this region here that we're going to model in some degree more detail. So for this analysis, I'm going to set up another study, but this one's going to be using the SOLIDWORKS Professional toolkit. SOLIDWORKS Simulation Professional, I should say. So with SimPro, I can run a thermal analysis. So actually, I'll go ahead and pick that guy, call this guy Pro Thermal. And with this one, you see quite a few more bodies I'm including here. But like I said, I don't really need that fan, so I'll exclude that guy from the analysis, so I don't have to worry about meshing that one. Then what I like to do is set up how, first of all, how the bodies are all interconnected to each other, where the heat source is going to be located, how this thing is actually cooling, convection to the air. So I think it's usually best if I start with the heat source, and then we can kind of work through the setup from, starting with that heat source at the top. So with my thermal loads, I'll set up a heat power on this microchip body. I'll use that body filter once again to grab that guy. This will be generating 3 watts. Now the way this works is that 3 watts is going to be dispersed across the entire body. Now if you want to do more detailed modeling where you model in the actual precise source of it, maybe there's a little microchip that's embedded inside of here, you could go through that additional effort and get even more accurate results than what I'm demonstrating here. But for now, I'm going to assume it's kind of this 3 watts gets spread out over the body to heat it up. And then how does that heat escape? It's going to escape through convection. Through convection to the air, okay? Whereby I'll just select pretty much all these faces across the top here, and we'll show you a tool later on called a selection set to help speed up this, selections like this if you have to make this selection often. Okay? So that grabs all this stuff. And then also down here, the connector I have set up here will actually have some cooling applied to it too. I'll grab these 3 side faces. And you notice the body's transparent. As long as I hold down my shift key, I'm able to click directly on those faces without having to rotate to the perfect view. Shift key allows you to select transparent faces. And then for all these faces, I'm going to assume, and that's a big word here, I'm going to assume the convection coefficient is maybe somewhere around 50 watts per meter squared. And you saw with that hand calculation tool how big of a difference this assumption can make. So we got to be good at picking these numbers if we're going to stick with this tool in some circumstances. Okay, we're going to use that same 300 Kelvin temperature for the air, and then so that's the primary convection. Now there's going to be a couple other convection coefficients I'll create on the back side here. There's going to be slightly slower cooling going on. I'm going to use a convection coefficient here of 25, and also grab this back side face too, because this is a side that doesn't face that fan directly, so it's going to have a lower convection coefficient. And also the board itself. The board itself will get cooled a bit too. So I'll say the convection coefficient on this surface here maybe is a little lower. Maybe I'll do 10 for an average. Okay. And with that, now I have the cooling directions all set up. Now I just need to tell it how the bodies interact with each other as well. Now by default, it's going to be bonding everything together, just like we did in that structural study a moment ago. But instead, let me show you. I can set up these contacts a little more precisely. If I use a couple of component contacts, just to say, just this top region up here, this is all going to get bonded to each other, and I'll include these 3 guys in there too. So everything touching between these bodies, they're all going to get bonded. And then also the connector, the board, and these 3 little leads in the bottom, those are going to get bonded to each other. But the places in between, these connectors here and those guys, they're going to have a little bit of resistance because it's kind of a loose connection. It's like a spring-like connection. So it's more of a rough connection there. And so I can use a local interaction, a little contact set here, and I can use this tool to automatically find some of these regions where they're touching. So find me the touching faces in this region here. You can see highlights for me, and in that region I want to apply a little bit of resistance to heat flow. Okay, 0.01 I'll use for my resistance. Okay. And I'll do the same on the between the connector and these 3 bodies as well. Let me show you what these ones look like. Tell it to find those. Okay, so it finds those touching regions. Okay. A little tricky to see, but I'll show you a little tool that allows me to visualize these. So let's see what I've set up there. If I use this tool here called the interaction viewer, you can get a sense of what I've just created. See, everything up here is bonded. Everything that's red is bonded, but then you see where there's thermal resistance in the region I just specified. Okay, just overrode that bonded contact in those little regions. All right, and with that, this study is pretty much ready to go. I'll go ahead and use the same kind of mesh I used before. I'll use that same blended curvature-based mesh, which I set as my default mesher. They've made some enhancements to that mesher in the recent years. It used to be one of the slower meshers to create meshes, and they boosted its speed in 2021, and then they've done a little more with it in 2022 as well. Produces pretty good quality elements, nice equilateral triangles for the most part. And I'll go ahead and run this thermal study. Thermal studies can be pretty quick to run compared to structural studies because we're only solving for 1 degree of freedom per node rather than 3. And it's already done. And I can see what are those temperature results. I'm seeing like 82.3 Celsius across these maybe across the top surface roughly. But really, now I want to take these temperatures and bring them into a structural study. And that's, how do I do that? Okay, how do I bring these into a static analysis? So for that, I'm going to set up my next step here, a static study. Same study I used before where I applied just those uniform temperatures. Okay. Since I'm using Simulation Professional right now, though, I'll call it Pro Static. Maybe bringing in those thermal results. And just like before, I'll exclude that fan body. Some of the similar setup. Same kind of thing with the connections as well. So nothing too new here, except what I'll do for the connections this time though is I can do things like key in friction to hold these things in place. So check this out here. Instead of the default for a lot of the stuff is bonding things. Now I'm going to use contacts, what formerly called no penetration contact, and I'll key in friction coefficient in these regions. Okay, for these three same surfaces there. And same thing on the other side too. We're just going to do friction holding this thing together. Okay, so that's all ready to go. And now I'll just leave the global bonded. These local contacts are going to override the global bonded in those regions for me. Okay, so everywhere else will get bonded. And then the fixturing. So this is where I wanted to show you a better way of fixturing some of these thermal studies. Because if I want to see the board bend, using that, remember I used roller slider before to try to restrain things. If I used like roller slider like I did before, like that board's not going to be allowed to bend. Okay? And if you want to see that board bend, we need to be a little more sophisticated with our fixturing routine. What I'll do is I'll just fix a point on the board like this. Okay? This is very common. This technique I'm about to show you, this fixturing routine is a very common one used in, it's actually used in our warp studies. When we run warp studies with SOLIDWORKS plastics, we select 3 nodes and it creates this type of fixturing scheme I'm about to show you here. But anyway, I'm going to fix this point, one of these points. But now you can picture the board and everything. It'd be able to pivot around that point, like that point is a ball joint. So I'm going to add another fixture over here. Okay. I'm going to restrain it in just 2 directions, not all 3. I'm not going to fix it entirely. So you can start to see, let me blow the arrows up so you can really see them. Okay, maybe even 300. So you can start to see what that's doing. It's going to allow this edge to expand and to bend. Okay. But now this isn't enough. It helps hold into place a little better. So now it's just not free to rotate about that ball joint. But picture there's an imaginary axis that connects this point to that one. This board is able to rotate around that imaginary axis. So we're going to add just one more fixture over here, somewhere off of that axis, and we're going to strain this in the direction depicted by this little green arrow there. So now you can see I'm now restricting it from being able to freely rotate. This is like the bare minimum fixtures you might want to add to restrain a model that's in relative equilibrium. Okay, just a fixturing scheme like that. I call it a 3, 2, 1 fixturing scheme because you're fixturing 3, then 2 degrees of freedom, then 1 degree of freedom. And we'll see what we'll take a look at what the results look like with that. Now, finally, the most important thing here is to import the thermal load, and I'll do that using thermal effects. Whereby here I can grab those pro thermal results that I just ran. You can see I have some other studies, all these other studies down here I can pull from. I'm just going to pull from that pro thermal study I just ran, and we're going to use that same initial temperature, 300K. And now this one, like the others, is good to go. So I'll use just for consistency, I'll use the same mesh. Now, arguably the mesh here, because this is a bigger model, the mesh is a little coarser, because the default meshing scheme is based on the volume or surface area of your overall model. So technically this is a slightly coarser mesh per capita, than what I'd used before. If I go and run this study, if I had just assumed everything was bonded together, the runtime here would be on the order of just a couple of seconds. Okay, I think when I bond stuff together, I think it takes around 5 seconds or so to run it. But because I used a more realistic kind of a sliding contact with friction, you can see that scales the runtime up by quite a bit. And many of you who've run some static studies already, you might already be familiar with this effect. Effectively, what I'm doing right now is running sort of a nonlinear study. It's what we call contact nonlinearity. Now, it's an important effect because if I just bonded this stuff together, we wouldn't see that this body here and that body there, they wouldn't be able to slide apart from each other a little bit like they'd in reality be able to do if things are expanding at different rates. If you bond them, you'd see a little more elevated. I guess you'd see more elevated stresses in some of those regions. Now, like I said, the study does take a little over a minute to run, so I'm expecting, even though it says 27.3%, usually it'll take big leaps to get to the completed step there. There we go, just as I say. And what was the runtime on that? It was about 1:18. So you can kind of see this about 78 seconds compared to if I bond them together. I think it takes about 5 seconds. And if I look at the displacements, and you know what I'll do here, so I can compare apples to apples, I'm going to delete these two plots. And I can bring them over from the static study. Remember, I spent all that time customizing the settings for these two guys. If I bring those settings over into my pro static study I just ran, now I can take a look at these stresses here. Compare apples to apples. So I want to look at these stresses. First and foremost, the key result I was looking at. And they look pretty similar to what I think I saw before. If I go back up and look at that same sensor, now I'm getting stresses like 91.8. They're actually a little higher than before. And my displacements, you remember seeing some black up here. And I don't see that anymore. Okay, I have the same scale set here. So it displaced by less. Okay, me including this extra stuff made it displace by less. That doesn't seem right, does it? Well, let me go ahead and launch the compare results tool, where we can put things side by side, make it a little easier to see what's really going on here. Okay. So I'm going to grab I can see I got all these studies set up from before, so I have to turn off those. But let me just grab these guys here, the standard static I set up and the pro static, looking at those stresses and displacements from both of those. Bring all that stuff in. And you can tell which is which. Obviously, the one that has the board on it is the pro, and the one that doesn't have the board is the static. Okay, so that's pretty easy to tell without even looking at the names. And maybe if I get these oriented about the same angle here, okay, see all the views are like linked together. Why is it that this one displaces by more than that one? And maybe you can kind of tell. It's the way this connector displays. The connector ends up helping us a little bit, where it kind of displaces it to the right, and it cancels out some of that displacement in the top here. So it's kind of neat. If you're worried about bumping into something over here, like I think they had those, they had to do a recall on some of the electric cars that were out there because of thermal expansion and things short-circuiting because of things bumping into other things. We can see this moves a little further than this maybe more realistic behavior. It's more detailed behavior. And then the stress levels, they look about the same, but if I look at you can kind of tell that, looks like this one spreads out a little thicker, that one's a little more, and it could just be a mesh thing. But really, the key thing to look at was that sensor that I had probing that surface for comparisons. So when I ran it just now, we got a result right around this 91.8. It was even bigger than the last one. Even with the conservative assumptions I tried to make, with the hand calculation, I guess it wasn't conservative enough. As I add more reality to it, the result just seems like it's going up a little bit more each time. So in this time, the reasoning for some of this increased stress is because now we're no longer assuming uniform temperatures. The temperatures are non-uniform, and those non-uniform temperatures, the internal temperature here being hot and then it being a little cooler on the outside, that adds to the stress. In addition to that, we are accounting for more complex heat transfer pathways too. We are allowing the heat to exit through this connector body, albeit through some thermal resistance. Oh, one more thing I forgot to show you. Let me go back to this. I want to show you the heat transfer as well. It's kind of nifty. So if I go back to the that thermal study for a moment, I wonder how much heat on this chip goes to the heat sink. In my hand calculation said it was like 3/4 of the heat. It was like 2.2 watts. Is it 2.2 watts that goes from here to the heat sink? What I can do to look at that is go back to this thermal study and probe the heat power. And it'll tell me it's not quite 2.2, it's more like 2.06. About 2.06 watts goes to that heat sink directly. All right. And another thing I can tell is how much heat goes out of the top of this guy here. All these faces that I put convection on, how much of that heat leaves out of those faces. Now for that, rather than me picking on all those faces again, what I can do is, and Sam will use this a little bit later too, I can create a selection set. If I click on this convection 2, I can save that as a selection set. So I can use that in other selections. So that way I don't have to repick those faces. And now if I come down here and I do another list heat power, now I can grab those faces from that selection set. Now it has a couple extras though that I don't want, and actually what I'll do for those is I'll just deselect them. Let me show these couple of bodies again so I can do that for you. Yeah, let me pick that selection set and deselect. I don't want to look at that one yet. I just want to look at these outer faces, and I'll turn that one off too. Okay. Let's see how much heat leaves out of here. About 0.68 watts leaves out of these surfaces. See that? You can kind of see what the distribution is then. We got about 2 going into the heat sink, about 0.7 coming out of these surfaces. That leaves a remaining of about 0.3, would be having, about 10% has to be going through this extra pathway that we just modeled, that it didn't model before in those hand calculations. Okay, so we can kind of probe where's that heat going, where can we improve some of these, if I improve this connection down here maybe in some way, maybe I can get more heat to flow take this pathway. Next, what I'd like to do is we're going to be running a flow simulation study so that we're not having to guess at these convection coefficients anymore. And so I'm going to turn it over to Sam at this point. He's going to show you the SOLIDWORKS flow simulation tool, setting up a quick flow simulation study, running that analysis, figuring out those convection coefficients, and then plugging that into a structural study. And then let's see what the results we get from this much more detailed study are going to be.
All right, so as Shaun alluded to, in this step I'm going to be talking about the flow simulation side of this and basically doing the thermal side of it that he did using thermal studies in Simulation Professional, but instead using the thermal capabilities inside of flow to get that data. And we'll see the benefits of that and some additional things that we can do on top of what the Simulation Professional can do. Inside of flow we can remove some of those extra assumptions. We can grab those convection coefficients from the solver. The solver calculates them for us instead of us having to do that, albeit educated, I guess, for those coefficients. And then we'll use those thermal results from the flow simulation, just like Shaun did, except on just a standard linear static study using Simulation Standard. So what I have here is it's the exact same assembly, but what we were looking at with Shaun, we didn't have the fan modeled in. And we do want this fan modeled in because, as he mentioned at the very beginning, we will be actually applying a fan curve to this fan, and that's going to be pushing the air, and that's what's going to be calculating the convection coefficients for us. So what I'm going to go through here is just first creating a new, we call it a project, or a study from scratch in flow simulation, and I'll just give this a name. I'll call it Flow Sim Live. And this wizard kind of takes us through some steps to just kind of define some of the study defaults. I'm just going to go through and change some of these unit characteristics to be reading our temperature in Celsius instead of Kelvin, and then angles should be in degrees instead of radians. We're running an external study. An internal study is more for like an enclosed shape, so think of things like maybe an electronics enclosure or like flow through a pipe, something like that. We're going to be doing an external study because we want that fan blowing on the solids. So that's an external study for us. We're also going to include heat conduction to include that as part of the flow study. We need conduction there. Brings us into our fluid definitions. We're just going to say air. Everything around the solid bodies we're going to say is air. And in the event that we don't, for whatever reason, define one of the solid materials, we're just going to define it as an insulator. That's just kind of a safety blanket for us in case we somehow miss something on the solid materials. Roughness, we'll leave that at 0. And then from here I just need to set my ambient and initial conditions, staying on that theme of 300K. Remember, I switched that to Celsius, so it does that conversion automatically for me. Everything else we'll leave as the defaults there. So there we've got our study defined, and we can see that in this gray box it's defining our computational domain. And what that's doing is different from the Simulation Professional Thermal in that the air around the body is actually modeled, and everything inside of this gray box is going to be modeled as air unless it's a solid geometry that we've defined in the SOLIDWORKS model. Usually it ends up being a little bit too big, and especially so just for demonstration purposes. We're going to make this a little bit smaller for the sake of solve time, and now I'm seeing I should have changed my units to centimeters instead of meters as well. I blew right past that one, because we're dealing with a little bit of a smaller space here, so I'll just go in and change that quick here. And what I'm doing here to change the computational domain size, you can't always go in and edit it, but what I'm showing here is it's the shift drag technique, and this is great because it kind of allows you to kind of eyeball it, and I like to flip my views normal when I'm doing this so I can make sure I'm capturing everything inside it, and I'm just going to kind of give it a close look. But what I'm doing here with the shift drag is you can see it's when I drag on one of the handles, it also drags the opposite handle on the other side to keep it symmetric. So that's a nice way to make sure you're keeping things nice and uniform. And if you want, you can be a little bit more elegant with it and manually type in the numbers if you like. I'm just going to kind of eyeball it here and get it to something that seems pretty reasonable. Also, I just like to point out here whenever I talk about computational domain, it is important to make sure it is big enough. For demonstration purposes, like I mentioned, it's probably a little bit too small if you're looking at doing a final type of run with really refined results, but what we have here, it's good enough, and it'll give us results in a reasonable amount of time. The reason why it's important is because you want to allow enough space for the flow field to really fully develop. Make sure that computational domain is big enough for a final run. As far as solid materials go, we can import that data right from the model here. Just right click on that, choose import from model, and it looks at the SOLIDWORKS model. That means that we're going to be working with the same stuff that Shaun did. That's important because we're doing a comparative study here, seeing how things are different between the different solutions. And also my tree does not have all the stuff that I need on it here. So we're also going to be adding in a fan, and this is what's going to be pushing that air around. So what we're going to be doing here is an external inlet fan. We're just going to define that face as the one that has that fan flow. And then we can go into our predefined, this is just, it comes out of the box with SOLIDWORKS. I'm just going to go and find one of the fans that we found worked well for this application, PAPS 405 here. All right, and then it gives us a nice graphic that we will be pushing air in that direction through that fan. All right, so next we need to put in that heat volume source, and again, I don't have that on my tree for whatever reason, it's not coming in. So I'll turn on heat sources in my tree so I can grab that and put a volume source on that chip, just like Shaun did. I'm gonna say 3 watts on that. We're trying to keep this as much the same as we possibly can. Go back into the definition and also grab some goals for this and talk about what goals are. Goals are kind of like a sensor. So Shaun mentioned that he had a sensor to track the stress on the body. In the flow simulation side, goals kind of act the same way. It's an area of interest where we can track particular parameters of interest. There's also a benefit in that it helps the solver find convergence, kind of helps it know where the critical information should be being gathered. So we're going to grab goals for both the maximum temperature and the average temperature across that entire chip body here. All right, and again, just like I alluded to this at the start here, I'm going to do some contact resistance on the connectors too. Just like Shaun did on those same faces. It's a little bit different in the flow simulation side of things. We're going to be going into our engineering database actually. And first I'm going to use one of these selection sets here to use the same faces that we did on the Simulation Professional thermal side of things. I have this selection set saved in my tree that goes in and grabs those exact same faces that were used before. Again, trying to maintain as much continuity between the two products as possible here. But going into the engineering database, just to kind of show how this is set up, we have a connector resistance set up as a custom contact thermal resistance, and this is kind of just a guess. It's kind of the same as what we've been alluding to with the hand calcs, and it's a conservative guess, so that it isn't perfectly conducting there. I looked at it in the database, but I didn't actually select it. There it is right here. So that's just a quick value that comes in on those faces for contact resistance. And then from here, I'm just going to add in a couple of more goals. So we already grabbed the two on the chip from the definition of the heat source, and I'm actually just going to rename these quick because I skipped a step on the name template to give these a more descriptive name. So I'll just do this a little bit more manually so we can compare the difference between the different goals when we get in and looking at our results. But what I'm also going to be curious about tracking is on the heatsink here. So we're going to be looking at also on that one a maximum temperature and the average temperature across that whole body as well. So I just find the temperature solid parameter and choose the average and max columns on that row. And then I'll use my name template here to give it a more descriptive name and call it a heatsink instead of the chip so we can tell them apart here.
In this next step, we're going to be monitoring the heat transfer coefficient on the surfaces using a surface goal so that we can compare to the heat transfer coefficient that we had estimated in some of the thermal studies. We'll actually see how close our thermal study estimates were.
So I have another selection set for that just to save myself the time of having to fly around and grab all those same faces. And then from here, we're ready to go ahead and mesh it. And let's just see what the default mesh looks like. Since that default mesh is what worked well for Shaun, let's see how it looks on the flow simulation side. And that just takes a second to load up. And we'll go in and grab a quick plot just to visually see how that looks. And I'm just going to check it on the XY plane and also use all faces here. So on this mesh plot, it'll give us a good look at how bad the mesh is using the default one. You can see that like on this circle here, it's basically modeling as a diamond. That's not very accurate. And just these cuboid cells are just a little bit too large to map to that geometry in a way that would be good. So that tells us right away that we should probably run some refinements if we want good, accurate results. So we'll go through that process quickly here. We're going to first go into the global mesh. That's what we just did. And actually, I'm going to hide that plot out so it's out of the way while I'm doing this. But show the basic mesh here, and we tested it out here that the basic mesh, it's kind of the starting point is good enough with just at the maximum level at 7 on the automatic type. And then from here, just looking at that basic mesh, we are probably going to need some local refinements too. So we'll do some advanced refinement on the bodies of interest over here using local mesh. This is kind of like a mesh control if you're more familiar with the structural side of things. But I'm just going to grab all these solid bodies, all of these connections, the connectors, basically everything except for the fan and the PCB. And these are just the parameters that we found best. So these are the solid, fluid, and then the fluid solid boundary refining cell. So it's going to refine it 2 more times on those regions refined this basic mesh that we're looking at here 2 times. And then on the advanced refinement, we found that the best numbers here for small solid features, refine it up to 4 times, and then for the curvature level, 3 is good, and the curvature criterion is 30 degrees here. And we found that that gets it nicely resolved, and we can visually see that here quick. I'm just gonna run the create mesh again so we can see how much better it is now than it was before. And that'll just take a second or two. So now looking at this mesh plot, we can see that we're getting some nice, good, solid refinement around here. So that plane coming through the middle, that's basically all just air. That looks well refined enough, and then we can see the local refinements up here in the red. It's going up to about 4 levels on a lot of these areas. So that looks pretty good. And from there, I'd say we are pretty ready to just let it run now. Let me check my notes, make sure I look good now, but yeah, we're ready to run it here. And with flow simulation, we get this really great preview window that comes up, and that allows us to, as it's coming up, it's going over on my other monitor. There it is. So what happens here in the preview window, it allows us to kind of set up some, and I did this all beforehand, so it's all set up nicely, but it's pretty easy to set up on its own. But what we get to watch as it's going through the iterations and trying to find that steady state result. We can see how the flow field develops and what happens with the temperature as well. And it also allows us to track the goals, which I got to add in here. And we'll see that as it goes through these iterations, the goals are going to kind of bounce around and be displaying in different results that aren't necessarily a steady state. So it's a really great way to monitor things, especially on longer solves where you don't want to invest a lot of time in a long study if it's not giving you results that are going to be accurate. So tracking these things in the preview window can be a really great way to catch something before it happens and know where some problem areas might be, or if you maybe need to refine the mesh in a certain area, something like that. If things aren't looking the way that you think that they should, maybe you need to change a boundary condition, something like that. And what the goal plot here is trying to do, it's using each one of these goals as criteria for determining what is a, quote, converged result, that steady state result. And you see this kind of rectangle crawling across the bottom of the screen, and what it's trying to find is basically a flattened out region within that rectangle to determine that it's converged. And we see here it took 71 iterations before it was able to find that ideal steady state result. And still even great, you get a lot of good information out of it. Right here we can see that average heat transfer coefficient that we had a guess on before. We guessed 50. The flow simulation calculated that out to be 55. But with those results now, we can go ahead and look at some post-processing things. Yeah, first thing, let's just look at maybe like a surface plot here, looking at our temperature distribution on the faces. So let's just look at solid temperature on all of these faces and see how that looks. So what we're getting here is the global maximum is 76. Yeah, it's a little bit cooler there. We'll see in a second once we port these thermal results back over to the structural simulation side of things and use that as an input. We'll see how that affects the stresses. We'll do that in just a second. But yeah, another good plot to look at, or a post-processing item, is a flow trajectory. That's kind of the eye candy. It's a really great way to visualize how things look. From a flow perspective, you get to see how the air is moving around the solid bodies, and what we'll see here is a lot of swirling that happens. And yeah, I'm going to use the parameter of velocity here just so we get some different colors in there. But yeah, that flow trajectory, we can see the swirling coming out of the fan, and yeah, on a couple of these lines we can see how it runs into the heat sink there, and hopefully it's coming through all right on the webinar and not too choppy. It looks pretty good on my side, but yeah, you can just kind of see how the airflow is, where the airflow hits the most often. So that's why the heat sink was so critical for us to not have to guess that heat transfer coefficient because there's so much air hitting that body, whereas you see on the backside those guesses of the convection values on the chip being on the other side, that guess isn't as critical because it's not transferring as much heat through convection because it's not getting as much air hit on it.
One more important plot to create is the heat transfer coefficient surface plot.
And yeah, this is the other kind of critical part. I'll bring this scale down to say, yeah, maybe like, I don't know, 75 or something, just to get it in scale. But then we can see that the heat transfer coefficient across these bodies are not uniform, which on the Simulation Professional thermal study, we had to apply that convection coefficient as a uniform number. So we see that even that isn't realistic. So we can see around the corners where we get a little bit more of that air shedding across that sharp edge. There's a lot more coefficient on these sharp corners than there is, say, on the backside or even in the middle of that heat sink. Quite a bit difference, about 25 from here going all the way over to ballpark 75, even higher than that on the edges. So now if I wanted to go back and take these thermal results with the, I guess, more accurate, less guessing, the heat transfer coefficient thermal results, all that I have to do is kind of reuse one of those static studies that Shaun used and just copy it, and then I'll just change the thermal load to be using mine.
And for the sake of time, we're going to disable the friction contact and just use bonded instead.
All right, so now it's going to treat all those as just the global bonded. Now I'll just go into the thermal results, and instead of using the temperatures from Shaun's thermal study, I'll grab it from my flow simulation. I got to go back and check which results file that is. Okay, so it read it in as this number 2. So go find that number 2 folder, grab that FLD, that's the results file for flow simulation if you're not familiar. Use that same reference temperature, and now we'll just let it rip and see what it does.
By turning off friction and using bonded, we will lose a little bit of fidelity in the displacement results. However, the stresses in the chip to heatsink contact region that we've been analyzing should be about the same. Also notice that the runtime on this one is a lot faster. Instead of taking 78 seconds like it took on my machine earlier, this time it only takes about 5. That means it was about 15 times faster in this case to run with a bonded contact.
So if we're looking at that sensor that Shaun used for the stresses, we ended up with 81.39. Yeah, there it is all together here. So that prescribed convection coefficient, we got rid of that assumption here, and we're really doing the best that we can from a assumption standpoint. We ended up with a much lower result on stress than we did with both with the hand calc plus structural and the Sim Pro thermal plus structural too.
Thank you, Sam. For wrap up, I just have a few more slides I'd like to show. We showed you guys quite a few different tools today. I know it can be a little bit of a whirlwind here, but let me kind of paraphrase for you a little bit about what we saw. We saw a lot of this guy here. This guy, Simulation Standard, static analysis. We ran all those stress studies that we ran. They all used this tool here. So if you're going to do thermal stress studies, this is likely going to be one of your main tools. Now it just depends on where do you want to bring those temperatures in from. Do you want to bring the temperatures in from a hand calculation and then run a static study? Do you want to bring the temperatures in from a thermal study and then run static? Or do you want to use flow simulation to do the work for you? Okay, and one of those big differences we saw was convection, those convection coefficients. We do offer, there's a 3-day SOLIDWORKS simulation class that goes over the static analysis, all those stress studies we ran, an additional 1-day class that talks about the thermal. That's a big topic in this Sim Pro extra day. If you're interested in learning more about flow simulation, we have a 2-day class offering for SOLIDWORKS flow simulation. For anyone interested in seeing bonus content from this webinar, please take a look at part 2 of this video. A link will be posted in the description below. If you'd like to see more content like this, please like and subscribe. If you have any questions, I try to answer your questions promptly in the comments section. Thank you for watching.